Science is all around us. Science is all around us. The air we breathe, the ground we walk on, the stars we gaze at in the night sky. Physics is the science of how everything moves and interacts. It's the rulebook for the universe. But sometimes the rules get a little mixed up. We hear something from a friend, we see it in a movie, or we just assume it's true because it feels right. These ideas can stick with us for years, becoming common knowledge. Common knowledge isn't always correct knowledge, but that's not bad. It's an opportunity to learn something amazing. These misunderstandings, these science myths, are everywhere. They're like little brain wrinkles that need smoothing with facts and experiments. The cool thing about science is asking questions. Why does that happen? Is that really true? How can we test that idea? When we challenge myths, we're not just memorizing facts. We become better thinkers. We learn to look at the world with curious eyes and a skeptical mind. This way of thinking helps solve all kinds of problems. Today we'll tackle the biggest, most persistent physics myths. We'll look at falling objects and the secrets of outer space. We'll put these ideas under the science microscope and see what's really going on. You might be surprised by what you find. Some myths seem so logical that the truth feels strange at first. But the universe is often stranger and more wonderful than we imagine. Get ready to update your brain's operating system. Let's bust some myths. By the end, you'll have awesome science facts to share, and you'll see how physics can change how you view the world. It's a world full of motion, energy, incredible phenomena waiting to be understood. Let's explore it together. You are about to become a myth-busting science champion. It's going to be great. Transition. Here's a classic you might have heard while looking at the windows of a very old building, like a medieval cathedral. The myth goes like this. Glass is a super-duper slow-moving liquid. Over hundreds of years, gravity pulls the glass downwards, making the bottom of the window thicker than the top. It sounds pretty cool, right? People point to the wavy, distorted glass in old churches as proof. But hold on a second. Let's use our science brains. If glass truly flowed like a liquid, wouldn't we see it elsewhere? What about ancient glass from Roman times? Egyptian times? We have glass goblets, beads, containers that are thousands of years old. If glass flowed, they'd be puddles in their museum cases. Instead, they're perfectly formed, unchanged for centuries. The real reason is simpler: how it was made. Old glassmaking wasn't precise. The crown glass process, a blob of molten glass spun into a large flat disc which produced uneven sheets. Glaziers cut rectangles from those sheets and usually installed the thicker edge at the bottom for stability. It was practical craftsmanship. So glass is not a liquid. It's an amorphous solid. Its atoms are jumbled, not arranged like a diamond or a salt grain. Being messy doesn't mean flowing. The atoms are locked in place. Any flow would be slower than the age of the universe, effectively zero. Next time you see wavy old glass, say, "Wow, old school glass making." Science rules. This is a famous saying, often used to suggest that a bad thing is unlikely to happen to you again. Don't worry, people say. Lightning never strikes the same place twice. It's meant to be comforting, a little bit of folk wisdom to make us feel safer. But when it comes to actual, real-life lightning, this piece of advice is not just wrong, it's dangerously wrong. The truth is, lightning absolutely can, and frequently does, strike the same place twice. In fact, some places get hit over and over and over again. Let's think about what lightning is looking for. Lightning is a giant spark of static electricity in the atmosphere. It wants to find the easiest, most direct path to travel from a cloud to the ground, or between two clouds. What makes a path easy? Being a good conductor of electricity and being tall. Tall, pointy, conductive objects provide a shorter, more convenient route. A skyscraper, a radio tower, a big tall tree on a flat plain is like a VIP lane for a lightning bolt. Consider the Empire State Building in New York City. It's a huge, metal-framed skyscraper pointing right up at the sky. It's a lightning magnet. It gets struck by lightning an average of 23 times every single year. Some years, it's been hit as many as 100 times. Scientists and photographers love it because it's such a reliable place to study and capture images of lightning strikes. The Willis Tower, formerly Sears Tower, in Chicago is another frequent target. So why does the myth persist? It likely comes from the seemingly random nature of lightning strikes in a wide-open area. But that's just probability, not a rule of physics. The physical reality is that lightning prefers the path of least resistance. During a thunderstorm, the safest place to be is indoors, not standing under the tallest tree. This myth feels so true, it's hard to argue with it. Take a bowling ball and a feather. If you drop them both at the same time, the bowling ball will slam into the ground while the feather gently wafts its way down. It's obvious. Heavier things fall faster. This idea has been around for over 2,000 years, dating back to Aristotle. He was a brilliant thinker, but on this one, his intuition led him astray. Then Galileo Galilei challenged the idea. Galileo famously dropped 2 spheres from the Leaning Tower of Pisa. The real science, the acceleration due to gravity, is the same for all objects, regardless of mass. On Earth, it's about 9.8 meters per second squared. That means for every second, speed increases by 9.8 meters per second. This pull is the same on a feather as on a bowling ball. Gravity pulls harder on the more massive bowling ball, but the bowling ball also has more inertia. These two effects perfectly cancel each other out. So why does the bowling ball seem to win? The culprit is not gravity, it's air resistance. Air resistance, or drag, is a force that pushes up on a falling object. It affects light, wide objects like a feather much more than dense, compact objects like a bowling ball. The feather has a large surface area and very little mass, so the upward push of the air almost cancels out gravity, allowing it to float down slowly. The bowling ball, on the other hand, is heavy and aerodynamic, so it slices through the air with very little trouble. You can try a version of this yourself. Drop them, and the book lands first. Now, crumple the paper into a tight ball. This doesn't change its mass, but it dramatically reduces its air resistance. Now drop the crumpled ball and the book at the same time. You'll see they hit the ground at almost the exact same moment. We've all seen the videos. Astronauts floating effortlessly inside the International Space Station, with tools and blobs of water just hanging in the air beside them. It's a phenomenon often described as zero gravity or zero G. This leads to the very common belief that once you get into space, you leave Earth's gravity behind completely. It's almost as if there's a magic line you cross where gravity just, switches off. But this picture, while visually compelling, is actually a total myth. There is actually a whole lot of gravity in space. Let's think about the International Space Station for a moment. It orbits the Earth at an altitude of about 400 kilometers. That's about 250 miles. At that altitude, the pull of Earth's gravity is still about 90% as strong as it is on the surface. If you could magically build a 400-kilometer tall tower and stand on top of it, you wouldn't float. You would feel only slightly lighter than you do right now. So, if gravity is still so strong, why are the astronauts floating? The answer is actually incredible. They're not floating, they're falling. The astronauts, the space station, and everything inside it are in a constant state of freefall. They're falling towards the Earth, pulled by its immense gravity. But at the same time, the station is also moving sideways at a tremendous speed, about 28,000 kilometers per hour, or 17,500 miles per hour. As it falls, the Earth's surface is constantly curving away. It's perpetually falling, but it never hits the ground. This continuous state of falling is what we call an orbit. This feeling of weightlessness is actually the same thing you would experience for a brief moment in an elevator if the cable snapped. Kind of a scary thought. Or at the very top of a roller coaster hill. The astronauts on the ISS are just in a much, much longer and more controlled version of that fall. So gravity is definitely in space. It's the very thing that holds the moon in orbit around the Earth, and the Earth in orbit around the sun. Without gravity, well, the whole universe would just fly apart. When we first learn about electricity, we're often given a simple analogy. A circuit is like a plumbing system. The battery is the pump, the wires are the pipes, the electrons are the water, flowing from one end to the other to power a light bulb. This helps us understand basic concepts like voltage and current. But this analogy creates a myth that when you flip a switch, a specific electron dashes from the switch all the way through the wire to the light bulb at nearly the speed of light. That's not quite how it works. The reality is much more like a tube packed completely full of marbles. The wires in your walls are already jam-packed with electrons, just sitting there in the copper atoms. When you flip the switch, you're not sending a new electron on a long journey. Instead, you're creating an electric field that gives a little push to the electron at the very beginning of the wire. This electron then nudges the one next to it, which nudges the one next to it, and so on, creating a chain reaction that travels down the wire incredibly fast. Think about it like this. Imagine that long tube of marbles again. If you push a new marble in one end, a marble almost instantly pops out the other end. The effect of your push traveled through the tube very quickly, but each individual marble only moved a tiny, tiny distance. This is what happens with electrons. The electrical signal, the push, propagates through the wire at close to the speed of light. But the individual electrons themselves, in what's called their drift velocity, move shockingly slowly. We're talking less than a millimeter per second. That's slower than a snail. So, when you turn on a lamp, the electrons that are already right there in the filament of the bulb are the ones that get energized and start to glow. They are nudged into action by the chain reaction that started at the switch. This is why the light turns on practically instantaneously. You don't have to wait for electrons to travel all the way from the power plant, from the substations, and down the wires to your house. They are already there, waiting for the signal to get moving. The water hose analogy is useful to start, but the real physics is even more interesting. Get on a merry-go-round or a spinning ride at the amusement park. As it spins faster and faster, you feel a powerful force pinning you to the outer edge. Everyone calls this centrifugal force. It feels real. It feels like an invisible hand pushing you outward, away from the center. The myth is that this outward pushing force is a fundamental force of nature, just like gravity magnetism. You spin something, and centrifugal force appears to push it away. It makes perfect sense, based on what we feel. But in physics, there's no such thing as a real centrifugal force. It's what we call a fictitious force, an inertial force. It's not a push. It's a feeling from your body's tendency to resist a change in direction. This tendency is called inertia. Newton's first law: an object in motion stays in motion in a straight line. Your body on the merry-go-round wants to fly off in a straight line, tangent to the circle. So what's really happening? The only real force is pointing inward, not outward. This is centripetal force. It's the force constantly pulling you toward the center, forcing you off the straight line your body wants to follow. On a merry-go-round, that inward force comes from the grip of your hands on the bar, the friction of your feet on the floor, the wall of the ride pushing against your back. That inward centripetal force keeps you moving in a circle. The centrifugal feeling is just inertia pushing against the centripetal force. To test it, imagine spinning a ball on a string. The string provides the inward centripetal force. If the string breaks, does the ball fly straight outward? No, it flies off tangent, in a straight line from the release point. It follows its inertia. So next time you're on a spinning ride, remember, you're not being pushed out, you're being pulled in. This is a fun one, feels like a bar bet or a schoolyard challenge. The myth is that it is physically impossible to fold any single piece of paper in half more than 7 times. Go ahead, grab a standard piece of printer paper and try it. You'll find that by the 6th or 7th fold, the paper becomes a thick, tiny, unyielding brick. It seems impossible to make that next fold. For a long time, this was considered an unbreakable limit. The science behind the difficulty is exponential growth. Each time you fold the paper, its thickness doubles, and its area halves. Let's start with a standard piece of paper, about 0.1 millimeters thick. After one fold, it's 0.2 millimeters. After two, it's 0.4 millimeters. After 7 folds, it's 128 times its original thickness, or about 1.28 centimeters thick. By this point, the paper is incredibly thick relative to its tiny surface area. The layers are bending over a very tight curve, requiring an enormous amount of force to crease. The myth exists because, with a standard sheet of paper and just your hands, 7 or 8 folds is indeed the practical limit. But the myth says it's impossible, and that's where it gets busted. The limit isn't a fundamental law of physics. It's a limit of the paper's size and your strength. If you have a big enough piece of paper, you can definitely fold it more than 7 times. This was proven in 2002 by a high school student named Brittany Galileo. She worked out the mathematical equations for folding and realized she just needed a much longer piece of paper. Using a giant roll of toilet paper almost 1.2 kilometers, or 4,000 feet, long, she and some volunteers successfully folded it in half 12 times. Her achievement, later repeated by the show Mythbusters with an even larger sheet of paper and an aircraft hangar, proves the point. The rule of 7 is not a rule at all. It's an observation based on a limited set of circumstances. It shows us how quickly things can grow with exponential progression and demonstrates the limits of materials. But it's not an unbreakable law. So, we've busted some myths today. We've learned that glass isn't a liquid. We've learned that lightning loves to visit its favorite spots. We've learned that gravity is all over the place, even in 0G. We've seen that electrons don't sprint through wires, and that there's no mysterious centrifugal force pushing us around. We even found out that with a big enough piece of paper, we can break the 7-fold rule. These myths stick around because they seem to make sense with our everyday experience. But when we dig a little deeper, we find a reality that is far more elegant, surprising, and amazing. Understanding the real physics behind these ideas does more than just help you win trivia nights. It changes your perspective. When you look at an old building, you can see the history of technology instead of a flowing liquid. When a storm rolls in, you have a deeper respect for the power of electricity and where it's likely to go. When you see an astronaut floating on TV, you can appreciate the incredible dance of velocity and gravity that makes an orbit possible. The world stops being a collection of mysterious happenings and starts becoming a system of understandable, interconnected rules. This is the true power of science and critical thinking. It encourages us to question the things we take for granted. It invites us to say, wait a minute, is that really how it works? And then to find out for ourselves. Every myth we've discussed today can be explored with simple thought experiments, or even real ones in some cases. Science isn't just for people in lab coats. It's a tool for every single one of us to better understand our universe. It fuels our curiosity and empowers us to be more informed citizens of the world. So keep asking questions. Keep being curious. Don't just accept that something is true because you've heard it a million times. Look at the world around you. The flight of a ball, the light from a lamp, the spinning of a toy top, and wonder about the physics that makes it all happen. The universe is a pretty cool place, governed by incredible rules that are just waiting to be discovered. The more we learn about them, the more we realize just how spectacular it all is. Now go out there and change the world with science.